Hello again. This is video lecture 10.4, and we're studying chapter 10, section 6, and we're going to introduce the concept of torque. And I'll give you first just a description of torque. Okay, this is the new quantity, torque. The description of torque is a measure of a force's ability to cause rotation about an axis. We are, after all, in chapter 10, studying rotation about a fixed axis. And we can think of lots of situations in the everyday world where we have rigid bodies rotating about a fixed axis. Probably the most common is a typical door, where you have a rigid body rotating about the axis of rotation that goes along the side where the hinges are. And so there we have rotation. And we tend to apply a force to the door, and our intent is to cause the door to rotate. And so in physics, we have a way, quantitative way, to calculate the tendency for a body to rotate when we apply a force to it. And this quantitative measure is called torque. Now let me start. It's going to be a little bit difficult with my limited video capabilities here, but let me try to show you real world what we're talking about, and then we're going to go to the diagrams on the slide. So here I've got this rigid pentagon, 5-sided polygon, and I've taken a screwdriver and just pushed it through one of the holes to make an axis of rotation. I'm going to try to keep it horizontal most of the time. And so it can, the thing can rotate about that axis of rotation. Then I've got a hole at one corner, and I've just passed a piece of string through that so I can hold on to it. I've also drawn in chalk a straight line from the axis of rotation out to where that hole is, because that's where the force I'm going to exert will act, through the string I'm pulling on. And all I want you to observe is that if I pull on the string, thereby applying a force to the piece of wood, I can cause the thing to rotate about the axis of rotation. Okay? Note, however, it may be hard again to see, if I pull on the string such that my force is lined up along the line that I've drawn with the axis of rotation, I don't get any rotation at all. But if I don't pull along that line, I can get the thing to rotate. So I can apply a force and I can get a rotation. And we want to be able to quantify how much rotation we can get from that force. So that's one way to think of torque. So now let's go to these pictures, this series of diagrams on the slide. First, starting on the left. The object is now kind of arbitrarily shaped. It's that kind of green blob. And think of it as being flat, planar, like my piece of wood I was just holding here. And it's got some little bit of thickness perpendicular to the plane of the screen. And we've passed an axis of rotation through it, coming out of the screen towards us. That's labeled O, and it's labeled there, rotation axis. Then out here on the edge in this picture is a point labeled P. And at that point, somebody is applying a force F with a particular magnitude in a particular direction. And you can see it's labeled in the picture F. All right, now there are a couple of important vectors that we have to note if we're going to calculate what's called the torque due to the force F about axis O. That's the language. The torque is due to a force about a specified axis. In this picture, the torque will be due to the force F, acting at point P, about the axis O. Two key vectors in this picture. A position vector R that points always, here's the definition of what we mean by R, from the rotation axis out to the point where the force is acting. And your book calls that R arrow. It's the position vector for the force. It points from the axis of rotation out to where the force is acting. The other important vector in the picture is the force. which is anchored at point P, because that's where the force is acting in this diagram, and it's got a particular magnitude and direction. This first picture on the left here shows one other important quantity in this setup, and it is an angle. What they've drawn is they've extended or imagined extending the position vector r out to such that it has a common tail with the force F. In fact, let me draw that. If I just slide the position vector r so that it has a common tail with point P where the force is acting, it would look roughly like that. The angle phi drawn in this picture is the angle between R and F when they're drawn with a common tail. Okay, so that's kind of the initial picture, the setup. Now the contention is that if this kind of disc-shaped blob of an object has a rotation axis through O, and somebody is out there at point P pulling with the force in the direction that you see, and then that's it, there are no other forces, that blob will rotate about the axis O. How can we quantify that tendency to rotate? Well, let's go on now to the second picture, the picture in the middle. Same blob, same rotation axis O, same point P with the same force. But now what we've decided to do is he said, you know what? Let's decompose the force into two components. One component parallel to R, that's that component right there. And the book calls it the radial component of the force because it's along R. And then another component of the force perpendicular to R. That's right there. And your book calls that the tangential component of the force because it's perpendicular to R. Note the right angle symbol right here. Still have that angle phi. It would still be right there. Now the contention is that it's only one of those two components of F that is causing this disc-shaped blob to rotate. You see which of the two components it is? Is it F radial or F tangential? You might want to think about that. Just go with your intuition, but think about it. You can pause the video if you wish. Again, the question is, of the two components of our force that I have drawn, the one we call the radial component and the one we call the tangential component, you can see them both in the middle figure, which of those two components is the one that would cause this disc thing to rotate? Okay, did you think about it? Did you come up with your prediction? Did you say it would be the tangential component? Okay, that's the component that will cause the rotation. The radial component will produce no rotation whatsoever because the line of that component lines right up with the axis. And you can never get an object to rotate with a force that lines up with the axis of rotation. Try to open a door by pushing with the force that lines up with the hinges itself. You may have to practice that a little bit. You can never get the object to rotate that way. So it's F tangential that's contributing to the rotation of this thing. All right, now what else contributes to the rotation? Well, one of the things is how big is that F tangential? Okay, what's the other thing? How far point P is from the axis of rotation. The farther away point P is from the axis with the given F tangential, the more rotation you can get, or the bigger the tendency is for the object to rotate. So there are two key things that are important for quantifying a tendency for an object to rotate. How big is the tangential component of the applied force? And how far is that acting from the axis of rotation? So I'm going to write that down now. Okay, I'm going to write it kind of right here on the slide, right near the picture. And I'm going to go ahead and introduce the symbol we're going to use for torque. Now remember, in Chapter 10, it's all about rotation. And all of the kinematic variables in rotation used Greek letters, letters of the Greek alphabet. Dynamic variables also use Greek letters. And in this case, torque is an example of a dynamic variable. So the symbol we're going to use is a Greek letter, a letter of the Greek alphabet. Okay? All right, I'm going to start right here with this scenario. So let me just kind of draw an arrow to emphasize I'm looking right here. And the symbol we're going to use for torque is a Greek lowercase tau. Okay? That symbol looks a bit like a T. Watch out for that. I don't know what else to say, but don't call it T. Don't think of a T. You'll be hopelessly confused. I draw the tau symbol like that. Okay? That is a symbol we're going to use for torque. So what I'm going to do based on this picture is say that. We're going to take that component of the force that's tangential to R, so F tangential, times the magnitude of R. How far are you from the axis? That's going to be our just intuitive way to think about quantifying tendency for rotation. The bigger that tangential component of the force and the farther it is from the axis, the more tendency to rotate you will get. Now let's look at that force diagram a minute. That F tangential can also be drawn right there. And then I see, just from trig, that that component, F tangential, is the magnitude of the force times the sine of that angle, phi. So now I'm going to write this as magnitude of applied force times sine phi times magnitude of R. And now what I'm going to do in my expression for the torque is just do some combining of terms. Okay? I'm going to write this as magnitude of F times magnitude of R times sine phi. Because you can certainly take these multiplied quantities here, and since those are each of those just scalar quantities multiplied together, there are three of them, magnitude F and magnitude R sine phi, you can multiply them in whatever order you want. Okay, so then I get this expression right here. So far, that's my working expression for how to calculate the torque due to the force you see in that picture. Okay, now I'm going to show you one more way to think about that torque calculation. And in fact, this third way is the way I'm going to tend to do it in this chapter. So now let's look at the third picture in this diagram. Okay, now we're going to just draw a slightly different version of the diagram. It's still the same scenario. You've got that disc-shaped blob, rotation axis O, that force F is acting at point P. You've got the force vector F, and you've got the position vector R that you see there in the diagram. All right? The same as in the other two pictures. But now what I'm going to do, and that angle phi that you can see, I'm going to introduce two more things. There is the so-called line of action of the force, and all you do is imagine extending in a straight line, both above and below, the force vector itself. And that extended force vector is called the line of action of the force. We need to be able to draw that in a diagram. We're given an object, we're given the axis, we're given the point P where the force is acting. We need to be able to draw the line of action for that force. Just extend the arrow of the force. All right, now we're going to introduce an important quantity in this third picture. It's called, this is its historic name, the moment arm. of the force. Moment arm. Here's all that means. The moment arm of a force is the perpendicular distance from the axis of rotation to the line of action of the force. Okay, so you're going to start at the axis O, and you're going to draw a line such that you hit the line of action at a right angle. And you have to be able to kind of sketch that in your drawing. In this case, it's right there. And I'm eyeballing it so that I get a right angle when that red line I just drew hits the green line that is the line of action. And that red line that I just drew that hits the line of action at a right angle is called the moment arm of the force. And your book symbol for moment arm is R with a subscript perpendicular symbol, because the moment arm is the perpendicular distance from the axis of rotation to the line of action. Now, note something. How big is that moment arm in that third picture? That distance drawn in red, that line drawn in red, how long is it? That R perpendicular distance. Well, you see the right triangle we've got in this new picture? The hypotenuse is R. One of the legs is R perpendicular, the moment arm. And the angle up here, phi, that we've been using, is also right here from geometry. Because those two those two angles, those arcs that I've drawn in red, are what are called vertical angles. And vertical angles are congruent. So if I just look at the right triangle that I see there, with R as the hypotenuse and R perp as a leg, and that angle phi, I see that the distance R perp is hypotenuse, magnitude R, times sine phi. Okay? This length right here is magnitude R, this length right here, times the sine of phi, that angle right there. But wait a minute, look up above. I've got the combination R perpendicular sine phi in my torque formula. So that is the moment arm distance, R perp. So we get another formula, another way to calculate torque. We take the magnitude of the applied force times what's called the moment arm for that force. That's going to be the way I'm going to tend to calculate it in this chapter. So let me now, having talked my way through all this series of pictures, let me now write down the formula we're going to use for calculating torque in this chapter. And first, I'm going to emphasize one, guess what? Torque is a vector. So it's got a magnitude and a direction. In this chapter, chapter 10, where we have rotation about a fixed axis, there are only two possible directions for the torque, clockwise and counterclockwise. So we won't have to worry too much. It won't be that hard to worry about direction. But let me start with the magnitude. Okay? This formula right here, kind of in the middle of the screen, is the formula that I'm going to use to calculate the torque magnitude. Note, I put the tau symbol in absolute values. So this formula is to be used for calculating the magnitude of the torque due to a given force. Okay? Magnitude of torque due to a force. I will take the moment arm of that force, R perpendicular, times the magnitude of the force. That's a pretty simple formula when you write it that way. We just have to be able to calculate the moment arm correctly. That's what people have the most trouble with. So you got to take the correct value for the moment arm for that force times the magnitude of the force. You'll get the magnitude of the torque. Notice then, the bigger either of these two numbers is, R perp and F magnitude, the bigger the torque magnitude will be. So we're going to spend quite a bit of time practicing calculating torque. Let me continue on this slide for now. Torque is a vector, as I just said. In this chapter, the direction is specified by a sign, positive or negative. How is that going to work? A torque that wants to cause counterclockwise rotation will be assigned a positive sign. Tau would be positive r perp times F magnitude. And a torque that wants to cause clockwise rotation is assigned a negative value. Tau would be written as negative r perp F. And you have to be able to tell from the context of the situation whether the given force is going to want to cause counterclockwise rotation or clockwise. For example, go back to this picture. Let's go to the very first one. The very first picture here on the left. Okay? You do have to be able to visualize for the given axis, the given point P, where the force is acting, and the given direction that the force is acting in. Which way would the object rotate? Okay, in a situation like that, just think of it this way. You've got this extended line R. If the force in a picture like this is above that line, you're going to get, like you see right here, counterclockwise rotation. The whole thing would rotate counterclockwise about O. If instead the force were below that extended line, like that, then you're going to get clockwise rotation. If the force is directly along the line of R, like that, you get no rotation at all. You see why? Because you have no moment arm. The line of action of that force passes right through the axis of rotation. So there is zero distance from the axis of rotation to the line of action. You have no moment arm for a force like that. No rotation at all. But above that line, if the force points above that line, like here, you get counterclockwise rotation. That'd be a positive torque. If instead the force was like this, below that line, you'd get clockwise rotation and you'd have a negative torque. This takes some practice to get used to. So let's go to a simulation on Wiley Plus. Okay? All right, in this case, let me show you. We are looking down from above on a kind of like a stick or a rod. And the axis of rotation, O, is that big black dot on the left end of the rod. And about 3/4 of the way along it, somebody is applying a force F, right? Pointing in that direction. It's kind of down and to our right. That's the applied force. Okay? And so that's the dark blue arrow showing the force. The light blue arrow is the position vector, R, that points from the axis of rotation out to the point where the force is acting. So I want us to quantify the tendency for this stick or rod to rotate as we look on it in this situation. I'm assuming that's the only force acting. So let me go back to my slides and let me get myself some writing space. Okay? And let me draw my own version of what we see there. Okay. There is the stick or rod. There is the axis of rotation, often labeled by your book O. Here's the point P, where somebody has come along and applied a force F. That means they're pulling at that point P, and the picture shows it roughly in that direction. So that's the applied force. Okay? I will tell you in this scenario that the magnitude of that applied force we're going to take to be 5 newtons. Now, the position vector R points from the axis of rotation out to where the force is acting. That would be labeled R arrow. So the picture starts with the two key vectors, F arrow and R arrow. And we do have to be able to understand how we draw those. How do we draw F? How do we draw R? Simple. F is anchored at the point P where the person or the thing is pushing or pulling. Okay? And R points from the axis of rotation out to that point P. Okay, I think that a rod or stick, looking down on it from above here, with an axis O at the one end, pulled on by a force at that point P in the direction you see, will rotate. Can you visualize which way it will rotate? Which way would be its tendency to rotate? That way, yes? Which would be clockwise rotation. You have to be able to visualize that. Let's quantify exactly how much torque we're going to get. Let me tell you one other piece, or two other pieces of information. The magnitude of that position vector R. How long is R? We're going to take that to be 0.750 meters. And then one more thing. Let me show it to you on the animation. It's marked, it may be a little bit subtle, it's marked as a black arc right there. It's an angle. We're going to call it phi. What I'm going to do is extend R and then mark phi so that you can see it right there. And so phi, I'm going to tell you, in this case, is 30 degrees. Okay, how do we calculate the torque? Well, we'll get the magnitude, then we'll get the direction. All right, here we go. The formula I just introduced for calculating the magnitude of the torque is to find the moment arm, R perp, times the magnitude of the applied force. Now, don't do this too fast. That R perp, you can't just say, oh, it's that R. It's 0.750 meters. Well, not necessarily. Remember what moment arm is by definition and from our series of pictures above. It is the perpendicular distance from the axis O to the line of action of the force. Oh, maybe we better draw that. Let's draw the line of action of the force. Remember, just take the force arrow and extend it. In this case, you're going to want to extend it this way. However far you need to, okay? That is called, let's label it, the line of action of F. Okay, now I'm ready to draw the moment arm. Perpendicular distance from axis to line of action. So it's a line that goes from O and intersects the line of action at 90 degrees. Now here you just sketch it. Do your best by eye. I think that's about it. And emphasize it's a right angle. And label it. That distance is R perp. That's the moment arm. Now, how the heck do we find that distance? Because we have to. Well, we use our geometry and trig. If I've got that angle phi that I've drawn there, I contend that this angle right here is also phi from geometry, because those two are called vertical angles, and vertical angles are congruent. Then I see from trig that this length right here, R perp, that length, is, because notice I have a right triangle, that length, which is the hypotenuse, magnitude R, times the sine of phi. R perp in that picture is magnitude R times sine phi. So let's get that number. Magnitude R is 0.750 meters. Right? And I multiply that by sine of 30 degrees. And of course, the sine of 30 is a half. So a half of 0.75 is 0.375 meters. There's the moment arm in this situation. So now let's get the magnitude of the torque. I take the moment arm, 0.375 meters, not 0.75 meters, not r, but r perp, because that's the important length for getting the tendency for rotation. And it's half of r in this case, r perp is. And the magnitude of of F, force, is 5 newtons. So I multiply those two things together, and I get 1.875, and the SI unit of torque would be Newton times meter. And the convention is not to call that a joule when you are calculating torque. Just call it Newton times meter. Now that's the magnitude of the torque. We're not done, because torque is a vector, so we have to account for its direction. So now I include the direction. And then I'll use the symbol tau with no absolute value, because I'm not giving you magnitude anymore. I'm going to include the direction. But the direction is just going to be specified by a positive sign or a negative sign. I look at that scenario. I look where the axis is. I look where point P is. I look how that force is pulling. And I try to figure out which way would the stick rotate about O, given the force. Would it rotate counterclockwise? Then the torque is positive. Or would it rotate clockwise? Then the torque is negative. Well, we already argued, or explained that we need to be able to visualize that it would rotate clockwise. That's a negative torque. So my final answer for the torque due to this force is negative 1.875 Newton times meter. Okay? And we have just done our first torque calculation. Now let me go back for just a moment to the animation, because I want to look at that a little more. So that's what we have going on in this scenario right there. The force is applied down and to the right, 30 degrees below the horizontal, with a given magnitude R and a given magnitude F, and we get a negative torque, and we just quantified it, negative 1.875 Newton meter. This slider up here at the top lets me adjust the angle of the force. So I'm just going to slowly adjust it. I want you to think about when the torque is going to be the most negative that we can get, the most positive that we can get, and 0. All right? So here we go. Let's go this way. You can see the angle is just given as a number there in degrees. .180 there. Notice that that's changing the line of action in the moment arm as I change the angle of the force. Okay, so as we swing all the way around like that with the direction of the force, when is the torque the most positive? When is it the most negative? And when is it 0? Most positive means you have the largest tendency to rotate counterclockwise. 0 torque means you have no tendency to rotate at all. Most negative torque means you have the largest tendency to rotate clockwise. Okay? I want you to play along with me here, and I want you to say most positive, 0, and most negative as I swing it around, and then we're going to say it together. Say it to yourself. Okay? All right. Right now we have 0 torque. Did you say that? Because there's no moment arm. When the line of action passes through the axis, no moment arm, no tendency to rotate. You can't get that rod to rotate by pushing or pulling on it like that. Here the torque is negative, isn't it? And in fact, there's the most negative torque situation. Note in that case, the moment arm, R perp, is the magnitude of R itself, 0.752. newtons, so that you get a torque of negative 3.75 Newton times meter. That's the most negative torque you can get. Torque is 0 here again, because there's no moment arm, no tendency to rotate. Okay, now the torque is positive. We have counterclockwise rotation and, oops, if I can get it, there is the most positive torque configuration. Because the moment arm is the biggest it can be, it's equal to the magnitude of R, and so you get positive 3.75 Newton meter. And it's still positive torque, it's getting smaller, and now we're back to 0 torque again. Okay? All right, so it's very important that you understand everything that's going on in that picture. All right, now I want to show you one more thing, and then we'll do one more little bit of practice. Here what I have, it's going to be kind of hard to see, is a kind of a stick with hooks along one side, along the length, and a handle at one end. And I'm going to take this 1 kilogram mass, I'm just going to hang it on the hooks. And my job here is to hold it by the handle end, but not let it rotate. Okay? Okay, now the axis of rotation in this case is along the handle towards you. But I'm holding it so that it doesn't rotate. So, although we'll learn why, it should seem intuitive to you that the net torque on this stick is 0. Now there's a torque from the weight of the mass hanging, and then I'm applying a torque as well. You have to balance. And here's what I discover. If I move this mass farther out on the stick, I'm having to apply a bigger counter torque. Put the same mass even farther out on the stick. And I really have to applying a big counter torque. And I don't even want to try to hold it out here very long. It's just a 1 kilogram mass. Oh, I can't even barely hold it level. Okay? Why? Why is it so hard for me to hold the stick level? Let's calculate some torques to figure out why. So let me draw. I think I have enough space here. Let me draw a schematic of the stick seen from the side. There's the circular and cross-section handle that I was holding. And then there's the length of the stick part itself. Let me draw that circular part just a little bit bigger so that we can see it better. Okay? All right, now the axis of rotation, let's be clear, is at the very, very, very center of that circular end. And that circular handle has some radius I'm going to call little r. And the stick has some length that I'm going to call L. And let's just look at the case where the mass that we were hanging at the end, just draw it as like that, is at the very, very end. Then, of course, because of gravitational force, there's F grav acting at the end point of the stick. Think of that stick as horizontal. I should have drawn it better than that. I contend that I had to apply an upward force, effectively right there at the grip where my hands were gripping. And it has to be up if I'm going to hold the stick at rest. I won't worry about the mass of the stick right now. It's considerably less than 1 kilogram. This was heavier. All right. Now what I contend is that the net torque, notice how I'm going to write that, tau net on the stick must equal 0. And there are two forces that are producing torques. The gravitational force is producing a torque from this thing hanging at the end, and my applied force from the handle is applying a torque. Those torques must be balancing each other. So one must be positive and one must be negative. I'll just denote them tau g We'll call that a gravitational torque from the weight of that hanging mass. And tau applied, the applied torque. And their total must equal 0. All right, now let's think about each one of those torques, because we need to be able to calculate those. First, let's do tau grav. Please, I urge you to not skip any of these steps. First, draw the line of action of the given force, or just extend the force arrow. Just go straight up and down. Okay? So you need to be able to do that. Draw the line of action. Then, draw the moment arm. That's the perpendicular distance from the axis of rotation to the line of action. And I'm sorry if my rectangle there doesn't look, because it should look perfectly horizontal. I say that because now I draw the moment arm. Right there, right angle, R perp. Okay, how to quantify that? And what direction is it? That's important too. Well, just look at the axis O, where it is, and just look at F grav. Don't worry about F applied. Just F grav. And think about where F grav is acting, which way it is pulling, and where the axis is. Considering F grav alone, which way would it cause the stick to rotate as we look at this picture? Clockwise or counterclockwise? Right? It would be clockwise. That's a negative torque. So when I write the expression for tau g, I start with a negative sign. And then what I write is moment arm, R perp, times the magnitude of the force. Well, that's mg. Okay? All right. I'm going to come back to that R perp in just a minute. Let's go on to the tau applied. Now, forget about F grav now and look at F applied. Do you see what its moment arm is? It goes from the axis out to the line of action of F applied. So now you have to draw the line of action for F applied. And then the moment arm is just right there. It's almost too small to see. And which way would F applied cause the stick to rotate? Notice the axis is to the left of it, and F applied is pointing up. Don't worry about F grav, just look at F applied. It would cause counterclockwise rotation. So that's a positive torque. And I need its moment arm. I'll put an applied on that. And times the magnitude of my applied force. And that total must equal 0. Now let's get that moment arm for the gravitational torque. What's the perpendicular distance from the axis of rotation to the line of action of F grav? Because that's what R perp is. Well, technically it's R plus L. And then what's R perp for the applied force? It's just the distance R. I'm going to take this formula now and solve it for my applied force. I want to know why I need to apply such a big force to hold that stick level. So you can do the algebra, solve for F applied. You get R plus L times mg, R all over R. So why do I need a very big applied force? In fact, why do I need an F applied that's much larger than mg? Because I contend I do. It's because, on the right-hand side, the number multiplying mg, R plus L, over R, is pretty large compared to 1. You see why? Because L is much bigger than R. So R plus L over R is much bigger than 1. It's because the applied force has such a small moment arm that I need a big force to get the necessary torque to balance the gravitational torque. Okay, so if you need a certain size torque, but you have a very small moment arm to work with, then you're going to need a big force. Conversely, if you need a certain size torque, but you've got a huge moment arm to work with, then you're not going to need a very big force. And there are a lot of examples in nature where that's true. A lot of the tools that people use to turn screws and so forth make use of this fact. It also explains the Archimedean statement from classical Greek times that if you give me a stick long enough, I can move the earth. Now, it's metaphorical, of course, but the idea is if you need to end up with a big torque, big enough to make a planet rotate, but you don't have a very big force just from your puny arms, you can still get a huge torque from a very small force if you can get a huge moment arm. Okay? So you can get a lot of rotation from a small force if you've got a big moment arm. And that's a very important concept to keep in mind. Okay, we're going to do a little bit of practice with torque, and then I'm going to leave you with a class engagement exercise. Okay. Now, we have a strength competition here. We have two weightlifters, Betty and Bob. They're attempting to rotate a slab of sheetrock. That's the drywall material that you put in your house. It's quite heavy. And we're going to put this piece of sheetrock on a horizontal surface, and it's going to be hinged to rotate about a vertical axis, and we have an overhead picture in this figure here. So that weird shaped blob is the sheetrock. And there's the axis of rotation, right there, the big dot labeled axis coming out towards us. Okay, Betty applies a force labeled F1. So here's Betty's force, right there. Well, I didn't do a very good job at that, did I? F1 is Betty's force. And Betty produces this force by pulling on that peg right there that's built into the sheetrock. Bob's force, F2, is right there, pulling on a different peg that he has available to him right there. The magnitude of the position vector for each force is tabulated in the figure. There's the position vector for Betty's force, R1, and we're given its magnitude, 0.750 meters. We're also given the magnitude of F1, 100 newtons. There's an angle phi1, you see it in the picture there, we're told that's 15 degrees. Then there's a position vector for force 2. It goes out from the axis to where F2 is acting, it's right there. That's labeled R2. We're told its magnitude is 0.250 meters, and that the magnitude of F2 is 75 newtons. Our job ultimately is to decide if the slab rotates in the direction of the torque from Betty or the direction of the torque from Bob. Turns out the person who is able to get the slab to rotate in the direction of his or her applied torque is the winner of the competition. So we'll start in part A. What is the torque tau 2, including sine, due to Bob's applied force? Let's just focus on Bob's force, F2. So let's call it tau 2. All right. Now, completely ignore F1 and everything to do with it right now. Look just at F2 and R2. Okay, see them in the picture? F2 here pulling this way, and R2 from the axis out to that peg where F2 acts. First ask yourself, which way would the sheetrock slab rotate given that force F2 applied at that point there? Completely ignore F1. I think it's pretty clear, given the axis and given F2, that F2 would cause counterclockwise rotation. So the torque tau 2 is positive. And we have to take the moment arm, R per 2, times the magnitude of F2. So now we have to find the moment arm for R perp 2. So you draw the line of action for F2, extend that arrow, and then draw the perpendicular distance from the axis of rotation to that line of action. But that just turns out to be, in this case, the whole length of R2, right? So that's the moment arm, R perp 2, plus magnitude R2 times magnitude F2. So that's 0.250 meters times 75 newtons. And you get tau 2 equals positive 18.75 Newton meter. Okay? And we've done part A. Part B, what is the moment arm for Betty's applied force relative to the axis? So now apparently we're moving on to Betty's situation. So I'm going to get rid of some of the drawing I've done so that we don't have a lot of distraction. Now we're focusing on R1 and F1. And we want the moment arm, R perp 1. Oh, let me make sure we can see that. Okay, R perp 1. You got to be able to identify it correctly in the picture. First, draw the line of action of F1. Just extend the F1 arrow. In fact, the picture already drew part of it, didn't they? All right, now draw the moment arm for F1. Draw the perpendicular distance from the axis to the line of action for F1. Do your best to get it to hit that at a right angle. It's going to be roughly like that. You see? And that's going to be R perp 1. And we have to be able to calculate that. Now, if you're struggling to see that, focus on that right triangle right there. R perp 1 is a leg, R1 is the hypotenuse, and there's the angle phi 1, which is 15 degrees. So R perp 1 is the magnitude of R1 times the sine of phi 1, just from trig. So 0.750 meters times the sine of 15 degrees. Sine of 15 degrees is not very large, so we're not going to get a very large moment arm. Only 0.194 meters. So we're not getting very much moment arm with Betty's applied force. But that's part B. Part C. What is the torque tau 1, including sine, of Betty's applied force? Okay, tau 1. So now completely ignore F2 and R2. Focus on F1. Okay? It might help if you extended the line of R1 just for visual reference. It goes on like that. Because we've got to figure out which way F1 would cause this sheet to rotate. Again, look at the axis. Look at where F1 is acting and which way it's acting. I contend if F1 is below that extended line I just drew in purple, you're going to get clockwise rotation. If it were above that extended line, you'd get counterclockwise. But it's below. F1 is below that extended line. We're going to get clockwise rotation. That's negative, isn't it? So tau 1 is negative R perp 1 times the magnitude of F1. So that's negative 0.194 meters. And the magnitude of F1 is 100 newtons. So that's negative 19.4 Newton meter. So which torque is bigger in magnitude? Tau 1. So the net torque will be negative. So the net torque will be will be clockwise. So the thing will rotate clockwise. Betty wins. Okay? All right, so let me leave you with a class engagement exercise, which is more practice on torque. You will enter this on Blackboard as usual. And it goes like this. We have an overhead view in this figure. We have 5 forces, all of the same magnitude. And they're acting on a merry-go-round, but the merry-go-round is a square. It's a strange one, it says. that is rotating about this point here, P, not at the center. Point P is a mid-length along one of the edges. Now you see the 5 forces. F1, F2, F3, F4, F5. Look where they're acting on the merry-go-round and in what direction. But they do all have the same magnitude. Note the axis is at point P. Your task is to rank these 5 forces according to the magnitude of the torque they create about point P, greatest to smallest. Okay, that is your job on the class engagement exercise. And that's all for this video.